Through 10 presentations so far, we have found out how the Louis Vuitton Foundation was constructed. The Louis Vuitton Foundation is an art museum located in Paris. It is inside the Boulogne forest, which is called the Lungs of Paris. At the request of Bernard Arnault, the CEO of LVMH, the client of the construction project, Frank Gehry, an eminent architect, designed this building. Frank Gehry has designed a unique, iconic, and bold building, a magnificent vessel symbolizing the cultural calling of France. He was inspired by ship sails, glass roofs, and 19th century French gardens and icebergs. The combination of these elements led to such a mysterious design. Respectful of a history rooted in French culture of the 19th century, he dares to use technological achievements of the 21st century, opening the way to pioneering innovation. It is a showpiece, not only of art, but of design and technology. From initial architectural research to unprecedented engineering, cutting-edge building techniques, combined with unique artworks, make the Foundation Louis Vuitton a dream come true for all stakeholders in the project. The general information on this LVF project is as follows. The Louis Vuitton Foundation was an undertaking of unprecedented architectural complexity, requiring countless technical and technological innovations with groundbreaking design and construction methods. In order to conform to Frank Gehry's design, the people involved in the construction work found solutions to numerous unprecedented technical challenges. From the initial conception of the project right through to its finishing touches. From now on, I'm gonna present to you the construction sequence and engineering issues of the Louis Vuitton Foundation, about the process from the art to the reality. In October 2006, the creation of the Louis Vuitton Foundation was officially announced. By an agreement reached with the City of Paris, granting occupancy of public land, the Louis Vuitton Foundation obtains a 55-year lease for a plot of 1 hectare on which to construct a building dedicated to art and creation. Planning permission had been granted in August 2007, and then construction began in March 2008. Let's start with the excavation. Boring test was conducted for the excavation. Engineers found the clay layer 6 meters below the ground. We were able to know the reason for that issue from the origin of site, Paris. There is a theory that one of the origins of the name Lutetia, which is the origin of Paris today, comes from the ancient Celtic word luteo, that means swamp. In fact, the ground of the city itself in Paris is not very solid. So it is difficult to raise the building high because Paris is the city built on swamp. Not only the existence of the clay layer, but also the asymmetric structure of the Louis Vuitton Foundation was a challenge for engineers. Due to non-symmetrical shape, a stress concentration section could be generated. Therefore, it is difficult to disperse bending moments and shear forces to the surrounding ground, which may ultimately cause cracks of the foundation. These conditions were challenging for engineers. To solve these issues, engineers used the floating foundation for construction. By using the floating foundation, the foundation could be constructed on the soft layer without files. To realize it, engineers have to consider that the soil volume under the ground and the weight of the building should be balanced. However, the ground heave also had to be considered that occurs when excavating. Engineers saw this as a new opportunity to develop 3D numerical modeling which considered temporal effect. By using Caesar LCPC and FEM analysis software targeting the ground and structure, they found a delayed but continuous heave, 1 centimeter. This is a figure that satisfies the design criteria for LVF. As a result, the actual construction process of LVF is as follows. First 15 meters of excavation was conducted with diaphragm walls to resist bending and shear forces associated with lateral soil loads. And then, construction of the floating foundation was the same as that of mat foundation. So the large stress could be distributed to the surrounding ground to maintain the balance of the building, preventing floating settlement. 2,600 mm thick reinforced concrete was used to allow uniform loads to be densely dispersed. The rest of the surrounding construction, not structurally linked to the main building, was founded upon reinforced concrete slab foundations of approximately 500 to 600 mm in thickness. Now superstructure of the Louis Vuitton foundation is ready to be built. After the construction of foundation, engineers began to construct the interior spaces of the building. Looking at the composition of the building, there are various spaces for the use of art galleries, such as 11 galleries and auditorium used as concert halls. Interestingly, unlike the exterior design of the LVF, which seems quite complex, the interior concrete mess was not much different from the shape of typical building. This was the client's request. And in contrast to Frank Gehry's strong design inclination, it has a fairly simple form. The spaces inside the building consist of a series of rectangular rooms at the center of the plane. Therefore, in most cases, it was not different from the construction of conventional reinforced concrete. Layouts were drawn to ensure the rebars and molds can be placed correctly on the floor. And Euroform was used to help ensure that concrete is maintained in shape and gains sufficient strength during curing. For the progress of such construction, scaffolding was used to construct a high place that could not be reached by workers. By the way, as we developed 3D models of LVF, analyzed the construction of building, we found that there are few columns in the interior space, including the gallery. In order to figure out how did they build this structure, we guessed how the engineers could construct the interior of the LVF without using columns. We guessed that they used wall column structure because we could find out that interior space of LVF is the complex of simple rectangular concrete mess. About wall column structure, it is possible to transfer the load through the wall and create the space without using columns. That was the key concept for construction. Although the client's need was solved using a column structure, other solutions were needed for the comfort of the user's sound environment who would use the museum. The rooms of LVF require high noise prevention level, but wall column structure is vulnerable to the noise transmitted for the structure. So engineers used additional construction method. It is called floating floor system. Without using an additional mold, an air layer was made between slabs by using a spring system to block noise from the surrounding spaces. Because of the gap between slabs, it is possible to prevent the transmission of noise. And with the silicone finish, there's no inflow and outflow of indoor and outdoor air. That is how the engineers constructed interior space of LVF. Completion of the carcass and fitting of the iceberg's metallic framework. The interior space is constructed in the way is surrounded by iceberg and serves as a structural core of the LVF. Now it's time to go on to the construction of iceberg. Also, iceberg part is one of the major parts of Frank Gehry's design. As to the iceberg, construction can be largely divided into three: metal frames, aluminum panel, and UHPF-RC panel. In particular, UHPF-RC panel was chosen to represent the iceberg. In terms of material selection, we guessed that engineers selected fiber reinforced concrete as an exterior material because it is effective in expressing bending length thanks to its good toughness and it's capable of miniaturizing the cross-section of the member. About 19,000 ductile panels of bright white fiber reinforced concrete were attached to one iceberg. Installation of the ductile ultra high performance fiber reinforced concrete panels. To emphasize the curve of the building, each panel was spaced 10 mm vertically and 7 mm horizontally when installing the panels. To ensure that this interval is regularly maintained, each panel was robotically scanned and automatically positioned in the model to confirm correct design and fixation ahead of shipping installation. Thanks to the use of software, geometrically correct panels with joints and all necessary detailing were imported from Grasshopper into Tekla using Open API, causing almost no additional fine-tuning for each unique panel. Through the use of BIM, it was possible to eliminate possible misunderstandings among engineers and drastically reduce construction period and cost. Through this process, we knew that engineers had implemented iceberg designed by architects, but we had one question about the construction process. If there is a gap between concrete panels to emphasize the curved surface, water or vapor may penetrate through them. If so, wouldn't the material inside rust and ultimately reduce the strength of the structure? We considered this question because the decrease in the strength of iceberg, which acts as a structural core, is directly related to safety. And we were able to find the answer by looking back at the construction process. The construction of iceberg proceeds in the order of metal frame, aluminum panel, and UHPF-RC panel. Even if metal is well managed and coated, rust caused by water and the resulting change in strength is inevitable. However, aluminum becomes stronger and stronger by forming a thin and dense film on the surface through oxidation. So we thought that engineers attached aluminum panel between metal frame and UHPF-RC panel so that there was no problem of strength reduction due to corrosion, even if gap between panel exists. Engineers implemented that iceberg design intended by the architect, and the problem of corrosion was also solved by reflecting the properties of material in the construction process. Architect Gary wanted the building to look like a huge ship floating in the wide sea. Therefore, he sketched the shape of the ship's sail and created the design of the building. To design a building and then make it into a real building, engineers made it into a 3D model in a computer. Looking at the appearance of the LVF, it can be seen that it is quite complex and it was almost impossible to make it a 3D model. So architect Gary and his company Gary Technology made this possible by incorporating CATIA programs, which were mainly used in the aerospace industry, into architecture. Engineers created LVF buildings using various BIM tools such as CATIA, Tekla, and Grasshopper. BIM tools have helped express complex curved forms, work efficiency, and accurate calculations for structural stability. This is the sail of the LVF. There are 12 sails which are supported by the tripod structure and carry the load to the iceberg below. As the load at the fixing point of the building exceeded 1,000 tons, the constraints imposed by the basic structure of the building had to be responded, and in addition, the tripod and beam were selected as the support structure of the sail in consideration of the design aspect. The tripod consists of 100 mm thick carbon steel, duplex stainless steel hybrid plates, and nods. Because the architecture had to look like a huge ship according to Frank Gehry's goals, trees were selected as the material to support the edge of the sail that was most visible in the tripod. A total of 222 single and double curved glulam beams were used, and the maximum length of the wooden beam was 28.2 meters. High-strength polydenim containing duplex stainless steel was used as the steel that made up most of the tripod with wood. The reason why this steel was used instead of 316 stainless steel, which is more commonly used, is that it works well in more corrosive environments such as atmospheric conditions in Paris. And because the steel has twice the yield strength of 316 stainless steel, it was able to support a huge sail with a smaller amount, which reduced the tripod's load by 30%. After the selection of the material, each member of the correct size had to be connected in the air. But because the size of the material was huge, fine gaps or angle differences could lead to the collapse of the building. Delicate members connections were essential. Each factory-made member of the correct size is lifted with the crane in a suitable position. Afterwards, the angles of the two members are measured through a state-of-the-art machine for accurate engagement of the members, and the correct position of the members is taken in line with the 3D model, and the worker completes assembly in the air. Through this process, the tripod of exactly same type as the 3D model, which was designed geometrically and structurally, could be created. Since it was then necessary to create a frame for glazing, a secondary framework of wood and steel was added to the tripod to create a window frame. In addition, steel girders were constructed at regular intervals on the window frame to create a grid shape in which glass could be inserted. If glass is attached to this grid, it will have the same shape of sail as it is today. The sail covers a total area of 13,400 square meters, with the largest sail covering an area of 3,000 square meters and weighing 800 tons. And the surface of the sail is covered with 3,600 glass panels of the same size. Each of the glass panel surfaces constituting the sail has different direction from -90 degrees to 90 degrees. In addition, given the complexity of many aspects of the sail, each of the glass panel needs a unique shape. This was an attractive challenge for a multifaceted architecture and engineering team responsible for design, fabrication, testing, verification, and installation. However, the most important task among them was to create a unique geometric structure for each glass panel. The solution to this was a state-of-the-art glass bending machine that could bend reinforced glass panels to various ready without using molds, as the typical method of manufacturing curved glass was too expensive. Sunglass, a glass panel manufacturer, has geometrically optimized the existing glass bending machine for the perfect implementation of sails and is prepared to produce glass panels with 2 bending ready. Each glass panel was then manufactured to have a constant size of 1.5 cubic meter and was finally produced through a bending process to match the shape of the space in which the glass panel would be attached. With the placement of glass panels, the LVF building was completed. Starting with the challenge of the giant company Louis Vuitton and the great architect Frank Gehry, the constant effort of more than 400 engineers to select perfect materials, 3D modeling, and high-tech construction technology allowed the beautiful building Louis Vuitton Foundation to be built in Paris. In the future, better architectural technologies will be developed, and there will be constant challenges to architects and engineers. And we think we will be able to experience more great buildings in our lives. And I will finish my presentation by saying thank you to their efforts.